Hello, good evening.
Good evening, sir.
So do you have any doubt from last class in this
Yes, sir.
calorimetry part? Yes,
I had a
Gautam.
doubt. The latent heat formula, the Q is equal to M and latent heat, M into latent heat. I did not get how the formula came about.
This part
Yes, so the formula.
for
Only
latent
the formula.
perfusion.
Q is equal to M into L.
From where I have derived this part,
Yeah.
you don't need to know about it. You have to simply define, since latent perfusion constant, that is LF, which is nothing but amount of heat required to convert a fixed amount of substance, that is 1 kg mass, to change state from solid to liquid. So this LF equals to Q divided by mass. So I've just rearranged this particular relation to get Q. Is it clear?
Okay, sir.
Just see this particular term. In this particular definition, there is the amount of heat required to change 1 kg solid into liquid, or you can say the amount of heat required per unit mass to change its state from one to another is called latent heat. So amount of heat per unit mass is Q divided by M. Is it clear?
Okay, sir.
So if you move this M to left side, you will get Q equals to M times LF or M times LV, depending upon it is changing from solid to liquid or solid to gas. Any more doubt?
No, sir. Got it.
Let me define you the concept of water equivalent. In most of the case, or in most question, they will not give you the value of specific heat related to any particular substance. Instead, they will give you water equivalent. So let me define you its meaning. Suppose Q equals to mass times specific heat times change in temperature. I'm calculating in terms of water. Q equals to mass of any substance, specific heat of any substance times change in temperature. If these two quantity is equivalent to one another, so we can write mass of water, specific heat constant for water times change in temperature equals to mass of substance, specific capacity of substance times change in temperature. So this quantity and this quantity will cancel out. So if you calculate mass of water using this relation, you will get mass of substance, specific capacity of substance divided by specific capacity of water. This mass, which is equivalent in relation of specific heat of that particular substance, is termed as water equivalent. Is it clear?
Yes, sir.
So from this, we may write mass of substance times specific heat capacity of that substance must equals to water equivalent multiplied by specific heat capacity of water to get this particular product. Is it clear?
So this is how much amount of water you need to achieve the same cooling effect as a substance, right?
Yeah. So water equivalent is just comparison of mass times specific heat capacitance of that particular substance with respect to water. So instead of giving the mass of substance and specific of substance, they will just give you water equivalent. So just multiply water equivalent with a specific capacity of water. It will be equivalent to mass of substance times a specific capacity of substance. Minashi, is it clear?
Yes, sir.
Nabila, any doubt?
No doubt, sir.
Fine. Amount of heat is required to change the temperature of calorimeter of water equivalent 0.8 gram by 20 degrees Celsius. Try to solve using this above concept. Gautam, there is a little mistake in your answer. Minashi, you got any answer?
No, sir.
Okay. Since the amount of heat required to raise the temperature or change the temperature of particular substance is nothing but specific heat. So we may write Q equals to mass of substance, specific heat capacity of substance times change in temperature. This quantity in terms of water equivalent is equals to water equivalent multiplied by specific capacity of water times change in temperature. Nabila, is it clear?
Yes, sir.
Just tell me the value of water equivalent given this question.
0.8 grams.
Value of specific heat capacity of water.
20 degrees Celsius.
I'm asking about value of specific heat constant. That is S. Raza?
1.
Good. It should be 1 calorie per gram per degree Celsius multiplied by change in temperature, that is 20 degrees Celsius. So if you multiply this whole part, you will get 8 into 2, that is 16 calorie. Gautam, is it clear?
Yes, sir.
Now, if you have to further convert this particular quantity in terms of joule, you may write 1 calorie equals to 4.2 joule. Just multiply this above part, 16 calorie, by this 4.2 to convert into SI unit. Mazia, any doubt?
No, sir.
Okay. Good, Nabila. Good, Minashi. Okay, you all have written? Krishna, any doubt?
No, sir.
Okay. So this is all about calorimetry or exchange of heat or transfer of heat between two bodies or two systems. Let me define you the next part of this particular chapter, that is transfer of heat or simply heat transfer, in which first process is conduction. Suppose you have a conductor in which particles are arranged in fixed order like this. Now, if you raise the temperature of this end, let's say temperature of this particular end becomes T. So on raising temperature, will there be any change in thermal kinetic energy of particle attached to this particular end? So you'll say yes. According to the relation, kinetic energy equals to 3 by 2 kb into T. If you increase the temperature, thermal kinetic energy of particle at that point will increases. So initially, they will be vibrating to some smaller distance up to this point. But now on increasing their temperature, they will tend to vibrate to some larger distance like this. So on increasing thermal kinetic energy, vibrational energy of particle increases. So they will collide with its neighboring particle, and during collision, they will transfer some of their energy to them or with them. This transfer of energy will continue from one end to other end. This process of transfer of heat is called conduction. Gautam, is it clear?
Yes, sir.
Nabila, any doubt?
No doubt, sir.
So you'll say on increasing temperature, thermal kinetic energy of particle increases, which on collision with their neighboring particle transfer their sum of energy. This process continues till from one end to another end. This process of transfer of energy or heat is called conduction. Just write it down. You will have written?
Yes, sir.
1 minute, sir. So in the last line, what is it? Till from one to end.
From one end to other end.
Okay, sir. Done, sir.
Okay. Now this particular conduction, or for this particular conduction, let me define you. Basics of electricity you must have learned in class 10th. Electricity is basically flow of electric charges through any conductor. Next is heat current. Suppose you have a conductor consists of infinite number of free electrons in it, having length L, area of cross section A. So initially, if there is no any external voltage or source applied across its end, there will be flow of or movement of electron in this particular conductor due to their thermal kinetic energy. But in this part, net flow across any cross-sectional area must be zero. So we'll say there will be no flow of electron or current through any net cross-sectional area. Hence, we don't have any electric current in this particular part. But now, if you apply some source, let's say at this end and at this end, some voltage V1 and at some voltage V2. So you will say there is some potential difference across its end, V1 minus V2, that will be capable of flowing of charge from higher potential to lower potential, and hence current will flow from one end to other end. Is it clear?
Yes, sir.
So for the movement of electric charge through any conductor, we must need some potential difference across its end. Similarly, suppose you have conductor in which you have to flow heat current or heat through it. You must need temperature difference across its end. Let's say this is at some temperature T1 and the other end at some temperature T2. So there will be some temperature difference, delta T, T1 minus T2. This temperature will be responsible for flowing of heat current or heat from one end at higher temperature to the lower end at lower temperature. Is it clear?
Yes, sir.
Raza, any doubt? Okay. Next, for every object, if there is flow of current or charge through it, there will be some opposition caused or offered to that particular flow, which is called resistance. So you must have learned about resistance in your class 10th. R equals to rho L by A, where rho is resistivity, L is length of conductor, and A is area of cross section. This particular rho is reciprocal of sigma, which is called conductivity, or in terms of heat current, we may write it as 1 by K. So this K is called thermal conductivity, which is reciprocal of resistivity. So we may write resistance offered due to or inflow of heat current will be equals to 1 by K times L divided by A. Minashi, is it clear?
Yes, sir.
Next is amount of current flowing through this particular conductor. So next is current, or simply electric current. I equals to rate of flow of charge. It means charge flowing divided by time taken is called electric current. Similarly, we may define heat current represented by H as heat flowing through any conductor per unit time. Mazia, is it clear?
Yes, sir.
Okay, first write it down to this part.
So how is 1 by sigma equal to 1 by k?
This particular rho is resistivity, which is opposition property of this particular conductor, which is reciprocal of conductivity. So conductivity is in terms of electricity. So I've taken conductivity in terms of thermal or heat. So it will be replaced by K. So this is just equivalent in terms of heat term. Gautam, is it clear?
Yes, sir.
Sigma is electrical conductivity. And K is thermal conductivity. You all have written? Minashi, done?
Yes, sir.
Raza, Mazia, done?
Yes.
Okay. Gautam, just tell me, what do you mean by Ohm's law? You must have learned in class 10th.
Yes, sir. I think they, it tells that resistivity is a ratio between current and voltage,
Okay.
something like that.
Raza, tell me about Ohm's law.
Voltage across the two points is directly proportional to
Yes.
conductor.
directly proportional to the current flowing through it. Okay. So according to Ohm's law, we define potential difference across this particular conductor is directly proportional to current flowing through it. So it will be I times R, where R is proportionality constant, that is resistance. So we may write current equals to potential difference divided by resistance. If you put the value of R in this part, you will get sigma into A times temperature voltage difference divided by length is called electric current, which is nothing but flow of electric charge per unit time. Similarly, for heat current, we may write H equals to, according to Ohm's law, temperature difference divided by thermal resistance. Thermal resistance is L by K into A, so it will become Ka times delta T divided by L. And this heat current is nothing but heat flowing through any conductor per unit time. So it will be Q divided by T. Gautam, is it clear?
So I don't get the sigma A delta V by L, that thing.
I've just converted this particular row in terms
Okay.
of 1 by sigma so that you may relate these two different quantity individually. Okay.
Yes, sir.
Krishna, any doubt?
Yes, sir. Got it, sir.
You allowed down?
Yes, sir. Done.
Mazia?
Yes, sir.
Okay. Let me define you the concept of how to calculate resistance related to a particular conductor. Suppose you have a conductor which may have this dimension as X, this dimension as Y, and this dimension as Z. So if you have to calculate resistance offered by this particular substance, if current is going across this particular surface. So according to the formula, resistance equals to L divided by conductivity into A. In this expression, L should be always parallel to current, and A, it should be always perpendicular to direction of flow of current. Is it clear? Nabila, any doubt?
No doubt, sir.
So on the basis of this concept, try to find resistance offered by this particular cuboidal block. Which one dimension will be behaving as length and which dimension will be behaving as area? Minashi, just tell me which dimension will behave as length for this particular body.
Z.
Good. And for area?
Area. XI and Z.
Just see, this particular is direction of flow of current. So the dimension which is parallel to this must behave as length. So this will be Z. And the surface which is perpendicular to the flow of current, it means this particular part, which having length X, breadth Y. So the area of this particular surface will be X times Y. So resistance in the terms of this particular object will be Z divided by sigma X into Y. Raza, is it clear?
Yes, sir.
Gautam, any doubt?
No, sir.
Okay, just write it down. Now, on the basis of this above concept, let me ask you a question. Suppose this is slab having length 50 centimeter, 20 centimeter, and 20 centimeter. This end is connected to furnace, 100 degrees Celsius. This end is connected to ice, 0 degrees Celsius. If thermal conductivity of this object is 0.8 watt per meter per Kelvin. Now, on the basis of this, try to find first temperature difference, across its end. Second, temperature gradient. Third, heat resistance. Fourth, heat current. Fifth, amount of heat reached to ice in 1 minute, and using this heat, amount of ice melted. Just solve each part and send your answer. Gautam, any problem related to this part?
What's I doing?
Okay. Nabila?
No doubts, sir.
Okay. All of you just send me first 3 answer. Gautam, your third answer will be 15.625.
Yes, sir. I rounded it off.
Okay. Vamsi, just check your second part and third as well. Mazia, just tell me, what do you mean by temperature gradient? Minashi,
Yes, sir.
what do you mean by gradient? Just see this. I define you. Gradient is change in any quantity divided by its length. Minashi, is it clear?
Yes, sir.
So here we have temperature gradient. It means change in temperature divided by its length. Mazia, is it clear? Nabila, just send me your answer. Good, Raza. Raza, just try to convert each quantity in terms of their SI unit. Let me define you the first part. Temperature difference is higher temperature minus lower temperature. So it will be 100 minus 0, that is 100 degrees Celsius. And since we have connected across these two ends, so current will flow across this. So the dimension which is parallel to the flow of current would be taken as length. So length will be 50 centimeter and area of cross section will be 20 into 20. So temperature gradient is change in temperature divided by its length. Change in temperature is 100, length is 0.5. So you'll get 20 degrees Celsius per meter. Minashi, is it clear?
Yes, sir.
Try to find third, heat resistance, which is equals to L divided by K times E. We have length 0.5, thermal conductivity 0.8, area of cross section 0.2 into 0.2. So it will be 5 divided by 0.32. So if you solve this particular part, you will get 15.625. Length having unit meter, area meter square, and this K thermal conductivity watt per meter per Kelvin. So it will be Kelvin per watt. Krishna, any doubt?
No, sir.
Okay. Try to find rest 3 term related to this above part.
So how is the unit Kelvin by watts?
According to the relation, heat current equals to temperature difference divided by thermal resistance. So resistance equals to temperature difference divided by heat. Okay. So temperature difference
Okay, sir.
having unit Kelvin and heat current having unit watt. Fourth is heat current, that is H, which is equals to change in temperature divided by thermal resistance. We have calculated temperature difference as well as heat resistance. Just put this to value and simplify it. In fifth part, we have to calculate amount of heat reached to the other end, that is Q. So according to the relation, H equals to Q divided by T. So we may write Q equals to H multiplied by T. And in sixth part, amount of heat or amount of ice melted must equals to Q mass times latent perfusion. So mass of ice that will melted equals to Q divided by latent perfusion. Just convert the value of latent perfusion in terms of SI unit first and then simplify it.
Sorry, amount of ice melt in 1 minute, right?
Yes, so just take time to be 1 minute or 60 seconds. Good, Raza. Good, Minashi. Good, Raza. Good, Minashi. Let me give you some hint for this last part. Latent fusion constant is equals to 80 calorie per gram. So if you have to convert calorie in terms of SI unit, so it will be 80 multiplied by 4.2 divide by gram in terms of kilogram. So it will be 10 to the power minus 3. So on simplifying, you will get 8 into 42 into 10 to the power plus 3. Just put the value of latent fusion to be this part and this above expression. Now, will I just check your calculation? Delta T is 100 divided by heat resistance 15.625. So on solving, you'll get 6.4 watt. Next, for amount of heat reached to ice end in 1 minute, will be heat current multiplied by time, which is 60 seconds. So you'll get 384 joule. And for last part, amount of ice melted during this particular interval of time will be M equals to Q divided by latent fusion constant. Q is 384 divided by latent fusion is 8 into 42 into 10 to the power 3. So if you simplify it, you'll get approx 1.14 into 10 to the power minus 3, or you may write it as 1.14 gram. Gautam, any doubt?
No, sir.
Raza, is it clear?
Yes, sir.
I'm giving you just 2-minute break, then I will resume, okay? Okay. Now, suppose you have conductor this conductor having thermal conductivity 0.5 watt per meter per Kelvin. This conductor having thermal conductivity 0.8 watt per meter per Kelvin. Length of each is L. Area of cross section of this end is 2A. And for this rod is A. So you'll be asked to calculate temperature of junction. Okay, so for this part, let me give you some hint. First, you'll say, due to temperature difference, there will be some heat current flowing from higher temperature to lower temperature. So let's say first heat will be across this conductor to reach at this end T naught. So there will be heat current H equals to K A divided by length, temperature difference 100 minus T naught. Similarly, for the second part, heat current is H2, which will be equals to Ka divided by length, temperature difference T naught minus 0. Gautam, any doubt?
No, sir.
Okay. Now, according to the concept of series and parallel combination, what you will say about this particular arrangement? Is it series or parallel?
Series.
And we must have learned in class 10th, in series combination, H1 or current will remain same. So we can say current flowing through first conductor must be equals to current flowing through second one. So H1 and H2 must be equal to each other. Is it clear? So you will say, since rod are in series for which current remains same, so H1 must equals to H2. Now just put the value of H1, H2 in this expression, simplify it for the value of T naught. Minashi, is it clear?
Yes, sir.
Try to solve.
So difference is from where this heat is starting and where the heat is going, right?
From higher temperature to lower temperature.
Yes, sir.
According to the concept of potential difference, since current flows from higher potential to lower potential, similarly in this part, you can say heat will flow from higher temperature body to lower temperature body. Let me solve it. We have H1 as Ka divided by L. Temperature difference 100 minus T naught. H2 is Ka divided by L. Temperature difference T naught minus 0. Now put the value of K1, A1 on each variable part. K1 is 0.5, A1 is twice of A, L1 is L, temperature difference is 100 minus T naught. K2 is 0.5, A is length, temperature difference T naught. So A by L will cancel out. So you're left with 0.5 into 2, that will be 1, multiplied by 100 minus T naught equals to 0.8 into T naught. So we may write 100 equals to 0.8 T naught plus T naught, and that will be equals to 1.8 T naught. So if you want to calculate T naught, it will be 100 divided by 1.8. 18 into 6, 108, 18 into 5, 90. It will be about this. Gautam, is it clear?
Yes, sir.
Minashi, any doubt?
No, sir.
Krishna?
Yes, it's clear.
Okay. You all have written?
Yes, sir.
Done, sir.
Nabila, any doubt?
No doubt, sir.
Okay. Now, on the basis of this heat conduction, we have to calculate K equivalent or thermal conductivity equivalent in the case of series combination of rod or parallel combination of rod. What you did in class 10th for series combination of resistance and parallel combination of resistance. Okay. So next is combination of rod. Suppose you have having length L1 at temperature T1, thermal conductivity K1. Another rod of same area of cross section but of different length L2, thermal conductivity K2, connected at some temperature T2. Let's say temperature of this particular junction to be T0. Now, for equivalent part of this whole arrangement, this is at temperature T1, temperature T2. Thermal conductivity equivalent is K equivalent, and total length of this particular rod will be L1 plus L2. So this is equivalent part of this above arrangement. So we have to calculate K equivalent in terms of K1, K2, L1, L2. Okay. So you can say this particular arrangement is basically series combination. So this is series combination of rod. So first, heat current for first rod H1 equals to Ka divided by its length, temperature difference T1 minus T2. Raza, is it clear?
Yes, sir.
So if you calculate temperature difference from this part, T1 minus T0 will be equals to H1 L1 divided by K1 into A as first part. Similarly, for second rod, heat current will be Ka divided by its length times temperature difference T0 minus T2. So again, if you calculate temperature difference using this expression, you will get T0 minus T2 equals to H into length divided by K into area of cross section. Now, if we add these two equations, let's say this is equation first and this is equation second. So on adding equation first and equation second, left side term to left side and right side term to right side. So you'll get T1 minus T0 for the first part, T0 minus T2 for second part equals to H1 L1 divided by K1 into A plus H2 L2 divided by K2 into A. Krishna, any doubt?
No, sir.
Now T0 and T0 will cancel out since this particular is in negative and this term is in positive. So you'll get T1 minus T2 equals to H1 L1 divided by K1 into A plus H2 L2 divided by K2 into A. Let's say this is equation third. Nabila, any doubt?
Yes, sir.
No doubt, sir.
Yes.
So why is it T1 minus T0 and T0 minus T2? How do we know which one has a greater potential?
I have just assumed T1 to be at higher temperature and T2 at lower temperature. So T0 must be intermediate between these two terms.
Okay, sir.
Okay, just write it down till this part. You all have written?
Yes, sir, done.
Nabila, done?
Yes, sir.
Okay. Now for equivalent part, you can write H equivalent equals to K equivalent times area of cross section divided by total length, temperature difference T1 minus T2. So if you want to calculate temperature difference from this part, T2 minus T1 minus T2 will be equals to H equivalent times L1 plus L2 whole divided by K equivalent into area of cross section. Let's say this is equation 4. Now, since this particular arrangement is in series, and we know in series combination, heat current will be always same. So in series, H1, H2, and H equivalent will remain same. So we can write from equation 3rd and 4th, we have same term in left hand side. So we can compare the right side term as H equivalent, or you may write this H1, H2, H equivalent as just H. So this will become H times L1 plus L2 divided by K equivalent into A equals to H into L1 by K into A plus H into L2 divided by K into A. A and H will cancel out from both sides. So you're left with L1 plus L2 divided by K equivalent equals to L1 divided by K1 plus L2 divided by K2 as equivalent thermal conductivity of this arrangement. Mazia, any doubt?
No, sir.
Gautam, is it clear?
Yes, sir.
Okay.
So we solve for K equivalent here.
Yes?
Should we solve for K equivalent here?
No, just remember this particular formula only. So for any question, you have to apply this part. L1 plus L2 plus L3 so on to Ln divided by K equivalent must be equals to L1 by K1, L2 by K2, and so on to Ln by Kn. Okay?
Yes, sir.
You may generalize this particular relation as L1 plus L2 plus so on to n number of rods arranged in series. So it must be equals to L1 by K1, L2 by K2, plus so on to Ln by Kn, like this. Gautam, is it clear?
Yes, sir.
Minashi, any doubt?
No, sir.
Will I have written?
Yes, sir.
Mazia, done? Okay. Find key equivalent for this particular arrangement. Just use the above formula, put the values and simplify it. Minashi, just check your calculation. Raza, just check your calculation. Good, Krishna. Nabila, you're almost correct. Just check your calculation. Just check the place of decimal. Good. Gautam, you got an
Yes, I
answer?
got 4/3. 4/3.
Okay. Mazia, according to formula, L1 plus L2 divide by K equivalent, since we have two rods connected in series. L1 divide by K1, L2 divide by K2. L1 is 0.4, L2 is 0.1 divided by K equivalent, which we have to calculate. L1 is 0.4 divided by K1, which is 0.8. L2 is 0.1 divided by 0.6. So this decimal and this decimal will cancel out. This part and this part will cancel out. 4 in 2 times will be equals to 8. Now, if you take LCM of this particular term, you will get 6. 3 plus 1, 0.4, 0.1, it will be 0.5 divided by K equivalent. So 3 plus 1 become 4 divided by 6. Just cross multiplication, 0.5 into 6 equals to 4 times of K equivalent, or K equivalent equals to 0.5 into 6 will be 3 divided by 4. So it will be 0.75 watt per meter per Kelvin. Is it clear? Gautam, you got the same answer?
Yes, sir.
Okay. Minashi, any doubt?
Yes, sir. No, sir.
Okay. We all have done?
Yes, sir.
Similarly, we may find parallel combination of rod. So next is parallel combination. Suppose there is a rod of length L, thermal conductivity K1. Another rod of same length but of thermal conductivity K2 and connected to same temperature difference T1 and T2. Area of cross section of this part is A1 and area of cross section of this part is A2. So on equivalent, combined rod will have area A1 plus A2, but of same length L, equivalent thermal conductivity K equivalent connected to same temperature difference T1 and T2. Now, in parallel combination, let's say H1 will be flowing in this part and H2 in this part, and H equivalent in this particular equivalent rod. So in parallel, current or net current flowing will be sum of all individual current in this particular each rod. So we can calculate first H1 equals to Ka divided by its length, temperature difference T1 minus T2. H2 equals to Ka divided by its length, temperature difference T1 minus T2. Now for equivalent part, H equivalent equals to K equivalent A1 plus A2 divided by its length L, temperature difference T1 minus T2. Now, according to the concept of parallel combination, you will say total current flowing this in each individual rod must equals to sum of current flowing across its combination. So H equivalent must be equals to H1 plus H2. Put the value of each term in this expression and simplify it, you will get K equivalent. Is it clear? So if you put the value of H equivalent, you will get K equivalent A1 plus A2 divide by its length T1 minus T2. H1 is Ka divided by its length T1 minus T2. H2 is Ka divided by its length T1 minus T2. Now we have T1 minus T2 in both sides, L in both sides, so they will cancel out. So you're left with K equivalent equals to K1 A1 plus K2 A2 whole divided by A1 plus A2. So this will be a final formula for K equivalent in parallel combination. Nabila, is it clear?
Yes, sir.
Gautam?
Yes, sir. What if the lengths were different? They cannot
Yes.
be connected, but still, what if the lengths were different?
No, you will be asked only for equal length. If length is different, you have to take it as it is, L1, L2, and so on. According to this expression, you won't simplify it further.
Okay.